imagine you have a situation where you have a surface, okay, and we're going to send in a beam of light. Let's say we're coming from water to air. So here's my surface, here's my normal. Can you quickly draw in the angle, or what the beam's going to do, how it's going to refract?
Has multiple. Do you want me to check?
Just choose one. Okay, so you really have two choices, two main choices, right? It's either going to go A or B. A or B. Which one is it going to be? A. Okay, so it's going to go in the A. So remember, when we go from a high index to a small index, the angle increases. We bend away from the normal. Okay, so how does this change if I send in, if I increase the angle of incidence? So let's say I come in like this. How's that angle going to change? It's going to increase even more, right? So maybe it's going to go like that. The angle's still going to get larger. Now it will be larger than the blue, but it's going to increase its angle as well. What if I send in a beam even more? What should happen? Even more. Okay? Well, eventually what's going to happen is I keep increasing this angle of incidence. Eventually I'm going to reach the point where that angle is going to do what? It's going to want to refract at 90 degrees. And then the question is, well, what do you do when you go beyond that? And that's what we're going to talk about today, is what happens when you reach that critical point where it wants to refract at 90 degrees. What happens as you go beyond that? Okay? And so actually, let's go ahead and define that. So I'm going to draw one more. So this wants to refract at 90, this blue one. This angle is called theta C, and that stands for the critical angle. And that is the angle, the incident angle at which the refracted angle would be 90 degrees. So the question is, what happens when you go beyond? And that's when we reach this state that's called TIR, or total internal reflection. So any incident angle beyond the critical undergoes what we call total internal reflection. Or TIR. So yeah, so what's going to happen to it basically? Instead of refracting, what will happen? It reflects. Good. So all these beams, so the blue, the orange, the black, the dark blue, are going to refract at all these angles. You calculate it using Snell's law. But once you go beyond that, Okay, so if I send this red beam in here, it is no longer going to refract. What it's going to do is reflect. And at what angle is it going to reflect at? The same that it came in. So if this angle is 80 degrees here, then this would also be 80 degrees. And in fact, anything, let's say the critical angle is 75 degrees, then 75.000001 and above, all the way up to 90, is going to reflect. All those will reflect. Anything below will refract. Okay? So that's total internal reflection. Let's look at the names here. Obviously, reflection means what it means, reflection. Total means complete, 100%. If you recall, in all these other things, even though I'm drawing refraction, what happens to some of these beams of light? They reflect. So for example, maybe this blue one comes in at 45 degrees. Maybe 70% of it refracts and 30% of it reflects. Okay, so that'd be partial. It does both. And everything always does both. When you look in a window, you can see your reflection in the window at the same time you can see through it. However, once you've reached this critical point and beyond, how much of it is going to be reflected? Total, which means what? 100%. Okay? No refraction happens, nothing. So that's going to be, that's where that word total comes from. Okay? Let's go over what internal means. To understand internal, let's look at the reverse case. So here we went from water to air. What happens if we go from air to water? So I'll draw my beam. And how is this one going to refract? Towards or away from the normal? Towards the normal. So this will refract towards the normal like this. So I'm going to do the same thing that I just did. I'm going to start using some slightly larger angles. So if I use this one, this orange one, it's still going to bend towards the normal. So even though it's going to be larger than that blue one, it's still going to refract towards the normal, right? Well, what if I send in a beam that is a little bit larger than that? What's going to happen? Towards the normal. Still larger than the orange one, but towards the normal. Well, what if I send in a beam at 89.9999999999999 degrees? What's it going to do? It's going to bend towards the normal. So do you ever reach this point where it can't refract anymore? No. So that's why this case, you can never get total internal reflection. It's impossible going from air to water. So in order for total internal refraction to occur, you have to go from a large index to a small index. So that's what that word internal means. It's kind of like you have to come from inside water to outside of air. You can't come from the outside of air to the inside of water. So it has to happen on the inside. So that's what internal means. Okay, so I guess let's just write that. So theta 1, sorry, not theta 1, N1, how does N1 have to compare to N2? Has to be greater. So N1 has to be greater than N2 or else it won't occur. Now that doesn't mean partial reflection doesn't occur. As we've mentioned, partial reflection always occurs, but complete total internal reflection has to happen under these conditions. Okay, so let's derive the equation. The equation is pretty straightforward if you understand the concept. So what if I asked you, what is the critical angle? And let's just do for a beam going from water to air. Okay, so we want to know what is that point at which reflection occurs, total internal reflection occurs. So you just set up your equation the same. Oops, what am I doing? Right, so the first beam, if this is beam 1, it's going to refract. If this is beam 2, it's going to reflect when we reach 90 degrees. So we want to know what is that critical angle at which refraction hits 90 degrees. So we'll just use Snell's law. N1 sine theta 1 equals N2 sine theta 2. Okay, so what should our N1 be? The air, the water, right? Where we're coming from. What should theta 1 be? That's our theta critical, right? And what should N2 be? That should be air. Okay, this was air, right? 1. And then what should theta 2 be? 90 degrees, right? 90. So if you want a generic equation, it would be N1 sine of critical equals N2 sine of 90. So the critical point happens when refraction tries to be 90 degrees. Okay? So why don't you guys go ahead and calculate this for water? What is the critical angle for water and air? Sorry, yeah, that was from the normal. It's not negative. What's the sine of 90? 1, right? Okay, so your inverse sine 1 over 133. What is it?
48.7.
Sounds good. Make sure you can get that number. Just for fun, can someone go ahead and reverse the numbers? What if you tried to go from air to water with the math? Okay, so go ahead and try it. Plug it in, see what you get if you mess it up. What's your calculator do to you? So here's my index for, my critical angle for water. Here's my critical angle for diamond. In which of these is light more easily reflected? Is light more easily totally internally reflected in diamond to air or water to air? So notice what this means. 48.8 means anything beyond this is going to reflect. So that means from 48.8 beyond, this whole region right here is going to reflect. So approximately half the light. Like if it was at 45 degrees, it would be half. So approximately half the light. On the other hand, diamond, how much light is going to reflect with diamond? Okay, a lot of it, all the way from 24.4 and beyond. So anything beyond that 24. So a diamond is a more reflective surface than water, for example, or anything with an index smaller than diamond. So what does this mean about diamonds? Okay, so what's a diamonds? One of the reasons they're so popular is because they're very shiny. Well, why are they very shiny? So let's look at a diamond. So let's draw out a diamond here. This is what an ideally cut diamond would look like from the side, something like that. There's actually a lot of physics in diamonds. When I bought my wife her diamond, I checked out all the physics, learned it all, so that I could produce this or give her this most sparkly diamond possible, right? That was the goal. So anyways, let's go over what's going on with the diamond. So the light comes in like this, right? Here comes the light. And because the critical angle is so small, more than likely what's going to happen at the surface? It's going to reflect. And this surface, same thing. And so when you're looking at a diamond, what are you seeing? Here's your eyes right here, right? This is your eye looking at this face of the diamond. You're going to see the reflection. So if we send another light in, reflect, reflect, comes out like this. Reflect, reflect, comes out like this. So when you're looking at a diamond, you're seeing the reflection of the incoming light. And this is why it looks so sparkly to you, because of all these reflections that go on, right? So ladies, what happens if your man tries to give you a glass diamond? What's the index of a glass diamond? What's the index of glass? About 1.5. So what does that mean about its critical angle? Okay, is going to be a much larger critical angle, maybe about 45 degrees or so. So anyways, here comes the light. What's going to happen? It just refracts down the bottom, right? Here comes the light. What's going to happen? Refracts down the bottom. Here comes one. Maybe it reflects. You get lucky, and then it refracts out the side. So when you look at this, what are you looking at? You're not seeing the reflections. You're not seeing the sparkly things that come off of it. Yeah.
So like crystal glass had different.
So yeah, so this would be an index of like a 1.5-ish. This would be 2.42. Now hopefully your man's not that dumb, tries to pull out a glass diamond on you, right? But what might they try to pull? Okay, cubic zirconia. So cubic zirconia, CZ, right? Those have an index of about 2.1. So it's going to be shinier than glass, but it's still not going to have the reflective properties of a diamond. Yes. Opaque objects, they don't even allow light to transfer through them, or at least visible light to transfer through them. And so they still have an index, but it would be based on what kind of light passes through it. So for example, like right now, radio waves are going through us. Okay, they're not interacting with our matter. And so they would still refract as they go through us, they just wouldn't be absorbed. Question? They reflect as well. There's some reflection that happens, and some refraction as well. All right, what about, so let me go over one other application. Let's look at fiber optics. Fiber optics are basically just thin pieces of glass. They're so thin that if you look at them, it just looks like a wire. So you could take a piece of glass and just bend it. It's so thin. Some of you might have these if you have an optical cable in your surround sound system, hooking up your Blu-ray player or something to your stereo. It just looks like a wire, but it uses lasers or LEDs to transmit light through it. So normally if I just shoot a laser, let's say I want to get from here to here, right? If I just shoot a laser is going to go in a straight line, pretty much stuck with the straight line. However, if this is glass and we have air on the outside, well, I can send the laser through here And what's going to happen when it reaches the outside? We can capture the light, essentially. So light will just continually reflect, reflect, reflect all the way through. Okay, and you can end up with it over here. So this enables you, if you want to send a signal from here to New York, for example, you don't have to aim your laser straight to New York. You can just send it down a fiber optic, and then just like any other wire, you can communicate with New York that way. Okay, so that's a fiber optic. We're going to capture it. Now we usually use glass or some other derivative of like a glass. What would be a better fiber optic to use? Diamond fiber optic, right? So that would capture it even better. Now why don't we use diamond fiber optics?